So hi everyone, you can hear me right? Yay! Okay, so I am super pumped to be presenting at the first PyCon in Portugal. Yay! So thank you so much firstly for coming to my talk. There looked like there was a very tempting workshop that's competing in this time slot. So thank you for choosing the Cliff Notes version. So let's do an introduction. Most of you have probably heard something about all of the amazing language models that are coming out at the moment. This is a very hot time for language models. So maybe you've heard about how a Google engineer claimed that their Lambda chatbot model had achieved sentience. Or you've seen poetry written by GPT-3, or maybe you've tried out GitHub's Copilot. And you probably sat and wondered, how are these models created? And more importantly, how can you take raw text and turn it into something that a machine learning model can understand? So I have 30 minutes, so I'm going to be giving a whirlwind tour of two of the most common ways of processing text for language models, and also give a very brief demo of how you can do this in Python. And as we're going to be kind of clipping through this the code at breakneck speed, I will be sharing the notebooks afterwards. So if you want to access those, make sure you take down my Twitter handle or come find me afterwards, and I can share those with you. Okay, so to give a bit of context, I started in natural language processing around 6 years ago. And prior to that, I was in a very traditional health sciences background. And everything in health sciences is in a tabular format. So, basically you have each row representing some observation and each column representing some information. And in machine learning, we call those features. And what I've been taught is that models can only accept tabular data as an input. So let's look at an example. Let's say we're trying to predict whether a house sells or not. So we have all these feature columns. They represent things like the number of rooms, the distance of the house to the beach, the house age, things like that. So what we do is we get a model, and that model has a specific input node for each of those feature columns. So the first node is going to expect the number of rooms. The second will expect the distance to the beach, and so on. So I got really confused when I started looking at text data because things obviously look really different. So let's look at a couple of sentences. Let's say we're trying to classify whether these sentences are clickbait headlines or not. And let's say that our first sentence has 4 words. Summer's hot shoe trends. So we just feed those into the 4 input nodes in the model. But then the next headline is a bit different. The best Halloween costume ideas. What do we do with this extra word? We don't have an input node for it. And the thing is, even if the sentences were the same length, it doesn't matter. Models can't process raw text, they need numbers. So this is where vectors come in. All vectors are, in the context of natural language processing, is a conversion of a document into a number of feature columns. And these features capture or explain some of the meaning that's contained in that text. There are a few different ways of doing this, and in this talk I'm going to be showing you 2 popular ways of vectorizing text, and we'll see how well our text vectors can predict whether that news headline is clickbait or not. So the first approach that we're going to discuss are called word embeddings. So to explain these, let's take 7 words. Queen, king, girl, boy, woman, man, and tree. So let's say, as a thought exercise, we decide to try and manually group them in a 3-dimensional space. So let's say we decide to put king and queen close together, girl and boy, woman and man, and then we put tree off to the side by itself. So if we take the coordinates of these words in this 3-dimensional space, what we can see is we get some patterns. So in the first dimension, girl and boy are quite similar. So maybe this dimension represents something to do with age. In the second dimension, king and queen are quite similar but different from everything else. So maybe this dimension represents something to do with class or nobility. And then in that final dimension, all the people are similar, but tree is off by itself. So maybe this represents something to do with personhood. So what these values are for each word are word embeddings. And what they represent is the meaning of a word by grouping words that are similar and pushing words that are dissimilar far apart. So of course, we don't create word embeddings manually. That would be an absolute nightmare, especially if you have a huge vocabulary. What we do is we rely on word embedding models to do so. And these models learn these relationships by seeing how words are used in context. So in today's talk, we're going to be using my favorite of these models, Word2Vec, specifically the skipgram architecture, if you want to follow up and read about this later. And the way that this model learns these word embeddings is by taking all of the usages of your word in the training data and trying to predict which words are likely to surround it. So let's take the case of the word best in our clickbait data. So what we're going to do is ask our model to predict which word immediately precedes and follows best. So initially these guesses are going to be quite bad, but as the model sees more and more examples of sentence fragments that contain the word, it adjusts these internal weightings that it contains, and the guesses get closer and closer. So let's get to training this model. We take our first sentence fragment, and the word that precedes is the, and the word that follows is things. In our second example, we have the same pattern, but in our third example, it's preceded by the, but followed by Halloween. So what the model will learn based on these three examples is that the word most likely to precede best is the, and with a little less confidence, the word most likely to follow is things. So a very nice thing about Word2Vec models is the weights that it uses to make these predictions about the words that surround your target word become the word embedding. So now we have a word embedding for the word best. We then repeat this exercise for every word in our vocabulary, and that means we end up with a word embedding for each word in our corpus. So due to the way that this model is trained, it means that words that are used in similar contexts will end up with similar weights in their embeddings. So here you can see that the words best, worst, and funniest are all used in a similar context. That means that they end up with embeddings that have similar weights in each dimension. In contrast, you can see words like war, attack, and blast are used in dissimilar contexts. So in practice, what I've shown you are examples of word embeddings with 3 or 5 dimensions. In practice, they have more like 100, 200 dimensions in order to try and capture all of the nuances of the meaning. And in principle, we also don't really care what these dimensions mean. We just need the computer to understand, or the model to understand, how these words differ. So what we're going to do is go through a few different screenshots to show some code of how to implement a Word2Vec model in order to classify those clickbait headlines. We're going to be using obviously screenshots from PyCon. I'm from JetBrains, so obviously I need to use our tools. Okay, so we're going to start by reading in a training data set, and we're going to use that to both create our word embeddings and train our clickbait classifier. And we also have a validation data set that we're going to use to test out our clickbait classification model. We then need to do some light string cleaning before we start building our Word2Vec model. And this is because Word2Vec models are based on tokens. So we want to make sure that all the tokens that mean or that represent the same word are grouped together by the model. Finally, we process these headlines into a form that the Word2Vec model understands. So we do that here. And what you can see is we're just basically taking that clean text and splitting each headline into a list. So here you can see an example of the first training example and how it looks. We then train our Word2Vec model. So what you can see is we import this package here. So from GenSim, we import the Word2Vec module. And this is one of those models that's a one-liner to train. It's very elegant and simple. We input our training data, and we set a couple of parameters. The first is the number of dimensions that we want our word embeddings to have. So in this case, I've chosen 100. And we've also chosen to not include any words that are only used once, because it's hard for the model to detect patterns when it's only used once. And then what we do is train the model. It's really fast to train. And basically what we end up with is a 100-dimension word embedding for every single word in our corpus. So here is what our word embedding looks like for best. We can also do things like find out words that have the most similar word embeddings to a target word. So we use this most similar method, And what it does is it finds the words that have the most similar word embeddings. In our case, words like funniest, cutest, absolute, most. But the thing is, we don't actually want to, classify words. We want to classify documents. So we need some way of combining these word embeddings into a document embedding. So the simplest way of doing this is to average the embeddings of the words in each headline. So I'm going to be calling these document embeddings or headline embeddings. And what they're going to do is represent how similar the headlines are to each other, in the same way that the word embeddings represented how similar words are to each other. So you can see that we've done this here with this first function. What this function does is loops over every single word in a headline, checks whether we have a word embedding for it, because remember we did exclude some words that were only used once, and if so, it attaches it to a NumPy array. We then have this second function, which basically loops over every single headline in our train and our validation set when we apply it, and basically checks whether we've actually been able to find word embeddings for that particular headline. If so, it averages them. So now we have document embeddings. Let's see what they look like. And for this particular sentence, new insulin resistance discovery may help diabetes sufferers, we have a very similar looking document embedding to the word best. Okay, now we can finally train our model. We're going to be training a really simple neural net. Under this convenience function here, I've implemented like a really simple Keras neural net. I'm not going to get into it here because I have 30 minutes. So basically what the model is doing is taking those document embeddings as an input and whether the headline is clickbait or not as the output, as the target to predict. And what you can see down here is that we managed to get 95% accuracy. So the model is pretty good for a first pass, but the most interesting thing to look at with models is where they went wrong. So when we look at the headlines that the model incorrectly predicts, you can see that a lot of them are not necessarily about the specific subjects being discussed. Some of them are obviously clickbait and obvious misses for the model, but some are more about the tone or the messaging. So for example, this one here, watch footage of 2 sick men unraveling their turbans to rescue 4 drowning boys. That could be a non-clickbait headline, but the tone makes you think it's pretty clickbaity. And you can see a similar pattern where the model incorrectly classified these as clickbait. So for example, Samsung plus T-Mobile, phone with a real camera. So this is where our word-to-vec models tend to fail us. They're not very good at detecting different uses of words in context. And this is where our next type of model comes in. So let's say you have a sentence like, he went to the riverbank. And you have another sentence like, he has a bank account. The word bank obviously means different things in those contexts, but a word-to-vec model will project them onto the same vector. It can't disambiguate them. So this is where the latest generation of models come in, and these are designed to understand the meaning of a word in context. Broadly, they're based on a type of neural net architecture called a transformer model. Examples of these are the really famous ones at the moment. So GPT-3, Copilot, they're all variations of transformation architectures. And I'm going to give a really high-level explanation of how these models work in terms of transforming text. So let's start with an example sentence that we want the model to vectorize. He checked his bank account. So where we start is sort of where we left off. We transform each of these words into word embeddings. But what we then do is we add positional vectors to each of these embeddings to indicate their position in the sentence. So the embedding for he would be weighted to indicate that it's the first word in the sentence. Checked would be weighted to indicate it's the second word in the sentence, and so on. So these weighted word embeddings are fed into a mechanism called self-attention. So self-attention basically, exciting. Okay, so self-attention basically uses the information from these weighted word embeddings in order to understand how much attention it needs to pay to all the words in the sentence in order to get the meaning of a specific target word. So let's have a look at this. So let's say we want to take the case of the attention vector for the word bank. What the model is telling us is that we should pay the most attention to bank itself. So each of these indicate he checked his bank account. But it's also saying we should probably pay significant attention to also the words checked and account, because they're giving meaning to bank in this context. So what you end up with is a self-attention vector for every single word in a sentence. And what the model does is a process called multi-headed attention. So it processes this attention vector multiple times and then combines each of them and then runs a normalization process in order to get a final attention vector for each word. And this process of creating these self-attention vectors and normalizing is what's called an encoder block. So this leads us to the specific transformer model we're going to be using to classify our clickbait headlines, which is called BERT. Hence why I had a random picture of a Sesame Street character at the beginning of the presentation. So there are a bunch of different sort of riffs on this Sesame Street character names that started. The first one was Elmo, which is not a transformer model. I think my favorite one I've ever seen is Camembert, which is the French BERT model. Everyone's having fun with this. So BERT is a general purpose language model, and it can do a variety of natural language tasks. Do things like question answering, text summarization, grammar detection, and obviously interesting for our purposes, it can do text classification. So how is it able to do this? It's all to do with how BERT was trained. BERT was trained to do two tasks. It's fed in two sentences at the same time. And it's asked to firstly predict whether the sentences are in the correct order. This is called entailing. So it's asked to predict, does this sentence imply this sentence? It's also asked to predict missing words. So in the case of this particular sentence, this sentence does imply this sentence, and the missing word is likely to be French, because growing up in Paris implies that you speak French. So how does it do this? What we first do is tokenize the sentence, as you can see. And then what we do is we ask the model to create these positionally weighted word embeddings for every single word. We then feed these positionally weighted embeddings through a number of different encoder blocks. Then at the end of this model, the model is asked to make its predictions. So what it's asked to do is, as I said, predict whether the first sentence or predict whether the sentences are in the correct order, and also predict the likelihood of this being the missing word. So you can see this model is doing pretty well. It's predicted with 94% probability that it's the correct order, and that French is the missing word with a 98% probability. So again, as with word2vec, initially the guesses are really bad, but as the model sees more and more examples of how language behaves in context, these predictions get really, really, really accurate. And the side effect is these encoder blocks make really good representations of how language is used in context. So the original BERT model was trained on something like 3 billion words, and it's a titchy, tiny little model compared to like the big boys that we're dealing with nowadays. So you can imagine how rich those internal representations of language become. So you might be thinking, this is great, but we don't want to predict missing words or entailment. We want to predict whether our headlines are clickbait or not. So what we can do is something called fine-tuning. So we now have this model that has all these lovely encoder blocks, but what we want to do is we want to chuck out those layers that predict entailment and missing words and use it to predict whether our headlines are clickbait or not. So let's say we have this example again, the best Halloween costume ideas this year. Again, we tokenize that sentence, we feed it into the model, and we ask the model to retrieve those positionally weighted word embeddings. We then feed those through the already trained encoder blocks. Then what we do in the last layer is we simply ask the model to predict whether the headline is clickbait or not. And again, this last layer is not going to perform very well initially, but as it sees more and more examples, it will get better and better at making those predictions. And in fact, because of all the information contained up here, it doesn't need that much training data compared to the initial training process. Okay, so let's jump back over to the PyCharm screenshots. So again, we have a training and a validation set that I've read in. What we need to do is obviously tokenize this so we can pass it into the model. So what we're going to be doing is using a package called Transformers from a company called Hugging Face. If you've got any interest in NLP, you definitely would have heard of them. They are super cool. I have a bit of a nerd crush on them. So what we use is a method that they've created called Auto-Tokenizer in order to tokenize our sentences. So before I explain what this does, let's just see what it does. So we pass our training and our validation sets through this auto-tokenizer method. And you can see what we get out in return is 4 different keys. We have our text, so our raw text. We have the label as to whether it's clickbait or not. But then we have these 2 new fields, input IDs and attention mask. So what do these mean? Well, let's deal with input IDs initially. So the first thing that this tokenizer method does is, well, it obviously tokenizes the text. So you can see that in a similar way as we had with the word-to-vec model, we just have a list. Then what it does is it maps it to these IDs. Okay? The problem is that when you have sentences that are different lengths, these input ID lists are going to be different lengths. And I already told you at the beginning that is a no-no. We cannot have that. So you can see an example of that here. So what you can do is you can add a method called padding. And what it does is when you have 2 sentences of different lengths, it just adds zeros to the shorter ones to make them all the same length as the longest sentence. But this raises an additional problem. We now have a whole bunch of IDs that the attention mechanism is going to process like they're real words. But they don't mean anything. So this is where the attention masks come in. What we do is we have these attention masks that are the same length as your input ID vector, and all they do is have zeros where there's padding and 1 where there's legitimate IDs. These pass in pairs through the model, and they basically tell the attention mechanism, pay attention to this, ignore all of this. So what you can then see is, oh yeah, I've already explained that. So basically, we're pretty much ready to train our model. There's some additional code where we need to convert everything into tenses. Like I said, I'll be sharing the notebooks. Feel free to go through that. I just want to skip over it because it's not super relevant to the topic of the talk. So what we do is we import our model. So I'm using a model called DistillBERT, another little play on words. It's a smaller version of BERT, which is said to perform with pretty much 95% of the same accuracy, which is good enough for us. We import that DistillBERT method using this particular method from the Transformers package. What that says is we essentially want to classify the sequences. We want to use this for text classification, and we have 2 labels, clickbait or not clickbait. So please chuck out those last layers that you were using for your training purposes and instantiate new final layers which are used for classification. We then call our model. You can see that there's a little bit of pre-setup, you'll see it in the notebooks, but it's really, really simple to train it. And voila, we're up to 99% accuracy. So again, let's have a look at where that model is failing. Interestingly enough, some of them are still kind of obvious, but I don't know, I don't really actually feel that these 2 are clickbait. And then finally, this one really looks like clickbait, but it's apparently not. Same with this one. So the interesting thing is these models are now getting to the point where they can outperform human raters. This is actually like a fairly standard result for these latest generation models. And I find that kind of cool and a little bit creepy. But yeah, that's basically what we're up to with these models. And that's it for me. So thank you so much. As I said, I'm going to be sharing a notebook.
Thank you so much.